Some oceans do not shine beneath an open sky. Some oceans do not move with wind, or reflect clouds, or meet the shore with waves. Some oceans may never see a sunrise at all. They may be sealed beneath miles of ice, wrapped in darkness, hidden inside moons that look still and frozen from far away. And yet, beneath those quiet crusts, in places where sunlight is only a faint memory, there may be liquid water moving slowly through the interiors of distant worlds. Tonight, we are going to drift gently through the hidden oceans of the solar system, not as a story of certainty, because science has not confirmed life in these places, not as a story of fear, because these worlds are not here to frighten us, but as a calm journey into one of the most beautiful ideas in planetary science. That water, one of the most familiar substances on Earth, may be hiding in deep and unexpected places far beyond our blue planet. On Earth, the ocean is visible. It is broad and bright, a moving blue surface under weather, moonlight, clouds and stars. From space, Earth is unmistakably an ocean world. The sunlight glitters across the Pacific. Storms curl above warm seas. Clouds cast soft shadows on water. The atmosphere glows thin and blue along the planet's curved edge. And below it, the ocean wraps around continents like a living memory of the planet's history. The ocean shapes climate. It carries heat. It absorbs carbon dioxide. It releases water vapor into the air. It helps form rain, storms, currents, seasons, and the conditions that make Earth feel alive. It is so present that we sometimes forget how extraordinary it is. A liquid ocean exposed to the sky, stable across geological time, connected to rock below and air above, is not something we should take for granted. Earth's ocean is a rare and precious environment in everything we know directly. It is also the first ocean we ever understood, the first one we could touch, sail, map, dive into, and study. It gave us our first language for tides, waves, currents, salt, depth, darkness, chemistry, and life. But the more carefully we explored Earth's own ocean, the more it changed the way we imagined oceans elsewhere. For a long time, sunlight seemed almost essential to life because so much of Earth's living world depends on it. Plants, algae, and photosynthetic organisms capture sunlight and turn it into chemical energy, forming the foundation of many ecosystems, from forests to coral reefs, from grasslands to plankton-filled waters. The sun is central, but Earth's deep ocean revealed another possibility. Far below the waves, where sunlight never reaches, life can gather around hydrothermal vents on the seafloor. There, heated water rich in minerals rises from Earth's interior, and microorganisms use chemical energy rather than sunlight. Larger ecosystems can build around them in total darkness. This does not prove that life exists beneath the ice of distant moons. It does not mean that every hidden ocean is inhabited, but it widens the question in a powerful and peaceful way. It tells us that sunlight is not the only possible energy source for an ecosystem. It tells us that water, rock, heat and chemistry can create environments worth studying even in darkness. And so, when scientists look at icy moons far from the sun, they do not ask only whether the surface is warm. They ask whether there may be liquid water below. They ask whether that water touches rock. They ask whether there is energy. They ask whether chemistry has had enough time to become interesting. They ask whether a frozen world may be more alive with process than it appears from the outside. This is where the idea of ocean worlds begins to feel almost like a quiet door opening. An ocean does not have to be blue from space. It does not have to have waves under wind. It does not have to sit beneath clouds. It may be invisible, buried, silent, and still scientifically important. It may be held inside a moon, warmed by gravity instead of sunlight, insulated by ice instead of air, moving in darkness beneath a surface that looks lifeless and still. From Earth, let your imagination rise slowly into orbit. The blue planet turns beneath you, cloud systems drifting over ocean basins, continents resting like islands in a wider sea. Then Earth begins to shrink. The moon passes nearby, grey, cratered. Mars appears far ahead, red and dry, holding the memory of ancient water, minerals and valleys. The asteroid belt stretches thinly across space. And then, beyond the inner solar system, Jupiter grows larger in the dark. Jupiter is not an ocean world in the way Earth is. It is a giant planet, enormous and striped, made mostly of hydrogen and helium, wrapped in deep atmosphere and powerful magnetic fields. But around Jupiter are moons, and among those moons are some of the most intriguing ocean worlds we know. The first is Europa. Europa looks pale, smooth and delicate compared with many cratered moons. Its surface is covered in ice, crossed by long, reddish-brown lines, cracks, ridges, and regions where the ice appears to have been broken and rearranged. From space, Europa looks almost like a frozen ceramic sphere, a small, bright world marked by lines that seem to trace something deeper below. It has relatively few large craters compared with many older surfaces, which suggests that its surface has been renewed over time. Something has been active there. Something has shaped the ice. Something has erased or softened the record of impacts. The leading scientific view is that Europa likely has a global ocean of liquid water beneath its icy crust. This ocean would not be warmed by the sun in the ordinary Earth-like sense. Europa is far from the sun, and its surface is extremely cold. But Europa orbits Jupiter, and Jupiter's gravity is immense. As Europa moves around the giant planet, gravitational interactions flex its interior. The moon is gently squeezed and relaxed, over and over, across long spans of time. This process, called tidal heating, can generate warmth inside a moon. It is not fire. It is not sunlight. It is gravity doing work within a world. The same basic idea helps explain why some moons are more active than their small size or distance from the sun might suggest. In Europa's case, tidal heating may help keep water liquid beneath the ice, and if the ocean exists as scientists believe, it may contain more water than Earth's oceans, though hidden away in darkness, far below a frozen shell. The most compelling possibility is that Europa's ocean may be in contact with a rocky seafloor. That matters because on Earth, water interacting with rock can create chemical gradients and energy sources. At hydrothermal systems, reactions between rock, water and heat can support chemistry that is important for life. Again, this does not mean Europa has life. It means Europa may have some of the ingredients that make a place scientifically interesting: liquid water, energy, chemistry, and time. The correct feeling around Europa is not certainty. It is careful wonder. Imagine drifting above Europa now. Jupiter fills much of the sky, immense, softly banded, turning in silence. Europa's ice glows beneath you, pale and crossed with lines. There are no blue waves, no open sea, no clouds, no sound traveling through space. Only ice, shadow, distant sunlight, and the possibility of an ocean below. If you could descend toward the surface, the landscape might appear cracked and ridged, with icy plates and strange, disrupted regions. Some areas may preserve evidence of motion in the shell, perhaps places where ice has shifted, fractured, or been reshaped by processes below. The surface is a message, but not a complete one. It is like seeing ripples in a frozen lake and wondering what water once moved beneath. Europa teaches a quiet lesson that echoes through this whole journey. The outside of a world does not always reveal the inside. The surface may look frozen, while below it, something much deeper may be moving. A world can be bright and cold outside, and still contain a hidden sea. Near Europa, orbiting the same giant planet, is Ganymede. Ganymede is the largest moon in the solar system. It is bigger than Mercury, though less massive, and it is the only moon known to have its own magnetic field. From far away, Ganymede appears grey-brown and icy, its surface divided between darker ancient regions and lighter grooved terrain. It is not as smooth and bright as Europa. It looks older, more heavily marked, more complex in a quiet, layered way. Scientists believe Ganymede may also contain a subsurface ocean, but its interior may be stranger than Europa's. In a large icy moon like Ganymede, pressure increases with depth, and water can behave in ways that are unfamiliar from everyday life. On Earth, we know ice as the solid form of water that floats, because ordinary ice is less dense than liquid water. But under high pressure, water ice can form different crystal structures, some denser than liquid water, inside large icy worlds. There may be layers of ice, liquid water, high-pressure ice, and rock arranged like hidden geology beneath the surface. Ganymede's ocean may not be a simple sea lying directly on rock. It may be part of a layered interior, perhaps with liquid water sandwiched between different kinds of ice. This makes Ganymede scientifically fascinating, but it also reminds us to be careful with imagination. When we hear the word ocean, we picture Earth, blue surface, waves, shorelines. But an internal ocean on Ganymede would be a different kind of environment, shaped by pressure, chemistry, and ice phases that have no familiar equivalent in a beach or bay. It may hold a vast amount of water. It may be deep. It may be layered. But whether it has the right conditions for habitability depends on details that scientists are still working to understand. Does the water interact with rock? Is there usable energy? Are there chemical gradients? How stable has it been over time? These are not small questions. They are the questions that turn an ocean from a simple layer of liquid into a possible environment. Ganymede feels peaceful because it resists easy answers. It asks us to slow down. It asks us not to flatten every ocean world into the same picture. It asks us to imagine water hidden under ice, yes, but also water under pressure, water between layers, water as part of a structure built by gravity and time. A world can be large, cold, and distant, and still have architecture inside. A moon can be more like a nested set of worlds than a simple ball of ice and rock. Farther out from Jupiter is Callisto. Callisto looks ancient. Its surface is heavily cratered, dark and bright in patches, preserving scars from a long history of impacts. Compared with Europa, it appears far less active on the surface. It is farther from Jupiter and not flexed in the same strong way by orbital resonances. If Europa feels like a cracked ice shell with something restless below, Callisto feels like a deep archive, a surface that has been quietly recording the solar system for billions of years. And yet, measurements suggest Callisto may also have a subsurface ocean. If it does, that ocean would likely be buried beneath a thick icy crust, in a colder, quieter interior than Europa's. It may be maintained by internal heat, the insulating properties of ice, and substances dissolved in the water that lower its freezing point. Callisto is important because it stretches the category of ocean worlds. Not every hidden ocean has to announce itself through a young, cracked surface. Not every ocean world has to be strongly active. Some may be buried beneath ancient terrain, their presence suggested by subtle measurements rather than dramatic appearance. In this way, Callisto is a reminder that quiet worlds can still hold deep secrets. It also shows that the word ocean world does not describe one single kind of place. Europa, Ganymede, and Callisto all orbit Jupiter, but each may hide water in a different way. Europa may have a relatively accessible global ocean beneath a dynamic ice shell. Ganymede may hold water in complex layers. Callisto may contain a deeper, more ancient internal ocean. 3 moons, 3 interior stories. One giant planet shaping them from afar. This is the kind of pattern that makes the solar system feel less like a simple diagram and more like a family of worlds, each with its own private depth. Now let the journey continue outward, beyond Jupiter's immense gravity, across a darker, colder region of space, towards Saturn. Saturn appears with a softness that almost feels unreal. A golden planet, wide and pale, encircled by rings made of countless icy particles. The rings look smooth from a distance, but they are made of fragments, each one orbiting in silence. Saturn's system is full of moons, each different, each carrying its own history. Among them, one small icy moon has become one of the most important ocean worlds in planetary science. Enceladus. Enceladus is not large. It is far smaller than Europa, far smaller than Ganymede, smaller even than many worlds that once seemed more important. It shines brightly because its surface is covered in clean ice that reflects sunlight well. At first glance, it might seem like a small frozen moon with little to reveal, but Enceladus surprised us. Near its south pole, long fractures cut across the ice. These fractures are often called tiger stripes. From them, plumes of water vapor, ice grains, and other materials rise into space. Enceladus is not only thought to contain a subsurface ocean, it is actively sending samples of that hidden ocean outward, above its surface, into the space around Saturn. This is extraordinary. Europa hides its ocean beneath ice, and future missions must study the surface, and perhaps search for ways to understand what lies below. But Enceladus offers material directly into space. A spacecraft can fly through the plume and analyze what is there. The Cassini spacecraft did this during its mission in the Saturn system. Its instruments detected water vapor, salts, organic molecules, and other clues suggesting that Enceladus has a global subsurface ocean and possible hydrothermal activity at its seafloor. Again, this does not prove that life exists there. It means that Enceladus may have several ingredients that make a place interesting for astrobiology. Liquid water, organic chemistry, possible rock-water interaction, and energy sources. The difference between proof and possibility is important. Sleepy science should never turn a hypothesis into a claim, but possibility, when grounded in evidence, can be beautiful enough on its own. Imagine Enceladus now, small and white against the darkness, Saturn's rings stretching across the sky like a pale, luminous road. The surface is frozen, ridged and fractured. Near the South Pole, soft plumes rise from cracks in the ice, carrying tiny grains upward into space. Some of those particles help supply Saturn's faint E-ring, meaning this small moon is gently contributing material to a ring around a giant planet. A hidden ocean inside a moon feeds a delicate ring around Saturn. It is one of those scientific facts that feels almost poetic without needing to exaggerate it. A tiny world, bright as snow, breathing water-rich vapor through fractures into space. Enceladus is peaceful, not because nothing is happening there, but because what is happening is so graceful to imagine. A moon with a secret sea, sending small icy messages into the dark. The plumes also raise a deeper scientific question. If material from an ocean can reach space, then spacecraft can study an ocean without landing, drilling, or breaking through the crust. Future missions may one day sample such plumes with even more advanced instruments, searching for chemical patterns, organic molecules, isotopic ratios, and other evidence that could tell us more about the ocean below. This is how exploration works at its best. Not by declaring answers too soon, but by listening more carefully to what a world is already giving us. Enceladus is giving us clues, and those clues are drifting through space as ice. Farther out in Saturn's system is Titan, a moon unlike any other. Titan is larger than Mercury, wrapped in a thick nitrogen-rich atmosphere, with a surface hidden beneath orange haze. It has weather, clouds, rain, rivers, lakes, seas, dunes, and shorelines. But the liquids on Titan's surface are not water. Titan is so cold that methane and ethane can exist as liquids there. Its lakes and seas are made mostly of hydrocarbons. Methane can evaporate, condense, fall as rain, flow across the surface, and gather in lakes, somewhat like water does on Earth, but under alien conditions and at extremely low temperatures. Titan is the only world besides Earth known to have stable liquid on its surface today, but it is not Earth-like in any simple way. Its rivers are not water rivers, its rain is not water rain, its seas are not blue oceans under warm air. Titan's landscape may look familiar in shape, but chemically it belongs to another realm. This is what makes it so fascinating. Titan shows us that planetary processes can run without being identical. A river channel can exist without liquid water. A lake can reflect a dim sky and be made of methane. Weather can happen in deep cold. An atmosphere can produce complex organic chemistry far from the sun and beneath Titan's icy crust. Scientists believe there may also be a subsurface ocean water. This makes Titan layered in an extraordinary way. On the surface, there are hydrocarbon lakes and seas under an orange sky. Below the surface, there may be an ocean of liquid water beneath ice. A world with two kinds of liquid environments, separated by crust, chemistry, and temperature. Imagine descending gently through Titan's atmosphere. The sun is a dim glow filtered through haze. The sky is outlined. The surface below is dark and smooth in places, shaped by dunes and channels. Near the poles, lakes of liquid methane and ethane rest quietly. Their surface is smooth beneath cold air. It feels almost familiar. Until we remember that the chemistry is different, the temperatures are far lower, and water on the surface behaves more like rock-hard ice. Then, imagine far beneath that surface, below the frozen crust, a possible water ocean hidden away from the orange light. Titan is not one mystery, it is layers of mystery. Atmosphere, surface, organic chemistry, hydrocarbon lakes, ice, interior ocean. Each layer asks a different question. What chemistry happens in the haze? How do methane rains shape the surface? How deep is the possible water ocean? Does it interact with rock? Could material move between layers over time? Titan does not give one simple answer. It invites a long study. It invites patience. That is why it belongs so naturally in a sleep documentary. It is not a world of simple spectacle. It is a world of slow, atmospheric, layered wonder. A moon with lakes under haze, and perhaps an ocean under ice. A place where the idea of an ocean becomes even larger than before. Now, as we move through these worlds, it helps to pause and ask, what makes a hidden ocean possible so far from the sun? On Earth, liquid water at the surface is supported by a combination of factors: distance from the sun, atmosphere, pressure, greenhouse gases, ocean circulation, and the long-term stability of climate. But Europa, Enceladus, Ganymede, Callisto, and Titan orbit far from the sun, where sunlight is much weaker. Their surfaces are cold enough for water ice to remain frozen. So, why would water be liquid beneath? The answer is that sunlight is not the only heat source in the solar system. Tidal heating can warm a moon's interior when gravity flexes it. This is especially important for moons orbiting giant planets, where orbital resonances and gravitational pulls can create repeated internal stresses. Radioactive decay inside rocky material can also produce heat. Thick ice can act as insulation, slowing the loss of internal warmth. Salts, ammonia, and other compounds dissolved in water can lower the freezing point, helping water remain liquid at lower temperatures. Pressure changes the behavior of water and ice. Together, these processes can allow oceans to exist in places that seem too cold from the outside. The surface tells us only part of the thermal story. A frozen crust may be like a blanket. The deeper interior may be warmer than the outside suggests. This idea changes our sense of habitability. The old simple picture of a habitable world was a rocky planet in the right region around a star, where liquid water could exist on the surface. That idea still matters deeply, especially when studying planets beyond our solar system. But ocean worlds add another category. They show that habitable environments, or at least potentially interesting water-rich environments, may exist beneath the surfaces, far from direct sunlight. A moon does not need to look warm to contain liquid water. The world does not need an open sea to have an ocean. The surface may be frozen, but the inside may be chemically alive with possibility. Still, it is important not to move too quickly from water to life. Liquid water is important, but it is not enough by itself. Scientists think about habitability in terms of multiple ingredients. There must be water, but also chemistry, energy, and time. Water provides a medium for reactions. Chemistry provides materials and gradients. Energy drives processes. Time allows complexity to develop. On Earth, these ingredients have worked together in rich and visible ways. On distant moons, we do not yet know how they come together, or whether they have done so in ways that could support biology. An ocean may be isolated from rock by high-pressure ice. It may lack accessible energy. It may have chemistry that is too limited. It may be too cold, too stable, too separated, or too different from Earth in ways we do not yet understand. This uncertainty is not a weakness in the story. It is the story. The hidden oceans of the solar system are not interesting because they give us easy answers. They are interesting because they give us better questions. What lies beneath Europa's ice? How thick is the ice shell? Does the ocean reach rock? Are there chemical exchanges between surface and interior? What drives the plumes of Enceladus? What compounds are carried in them? What does the seafloor look like there? How long has the ocean existed? Is Titan's water ocean chemically connected to its organic rich surface in any way? How do Ganymede's high-pressure ice layers affect its ocean? How deep is Callisto's possible ocean, and how isolated might it be? These questions are careful, specific, and scientific. They are not rules. They are not stories invented in the absence of evidence. They come from spacecraft measurements, magnetic field data, gravity studies, surface geology, plume analysis, and physical models. They are part of the slow, patient work of understanding worlds, and future missions will continue that work. Spacecraft can map surfaces, measure ice thickness, study gravity fields, analyze plume material, look for organic compounds, and refine our models of interiors. Exploration is slow, but slow is appropriate here. The oceans have waited for billions of years. We can approach them carefully, mission by mission, flyby by flyby, measurement by measurement. This is the quiet beauty of planetary science. A spacecraft travels for years through darkness. It reaches a moon. It passes over ice. Instruments gather data. Radio signals return across space. Scientists analyze them on Earth. A model changes. The question becomes sharper. The world becomes a little less unknown. There is no need for science to shout. A faint signal can change the way we understand. A plume sample can reveal chemistry from an ocean. A magnetic measurement can suggest water beneath ice. A surface pattern can hint at the ocean below. The solar system speaks in subtle ways, and we learn by becoming patient enough to listen. Now imagine the ocean worlds not as isolated facts, but as a journey. Europa, bright and cracked, orbiting Jupiter. Ganymede, vast and layered, carrying its own magnetic field. Callisto, ancient and cratered, hiding possible water beneath an old surface. Enceladus, small and white, releasing plumes into Saturn's space. Titan, hazy and orange, with methane seas above and possible water below. Each one expands the meaning of the word ocean. Earth gave us the surface ocean. Europa gives us the ice-covered global ocean. Ganymede gives us the layered ocean. Callisto gives us the ancient quiet ocean. Enceladus gives us the plume-connected ocean. Titan gives us the world of two liquid stories, hydrocarbons above, water perhaps below. The word ocean becomes deeper with every moon. It no longer means only waves and sunlight. It can mean pressure, darkness, insulation, chemistry, and hidden motion. It can mean water sealed away under ice, moving without wind, never seeing stars, yet still shaping the world from within. There is something soothing about hidden oceans, because they ask us to imagine depth rather than noise. They do not flash, they do not demand attention, they are not visible at first glance. They wait beneath surfaces, reminding us that reality often has layers. A person looking in Europa might see only ice. A scientist looking carefully sees cracks, patterns, induced magnetic fields, and the possibility of an ocean. A person looking at Enceladus might see small white moon. A spacecraft flying through its plume detects signs of water and chemistry from below. A person looking at Titan might see only orange haze. Radar reveals lakes, dunes, river channels, and a surface shaped by alien weather. Science is the art of looking more deeply without losing calm. It takes the visible world and asks what lies beneath. And with ocean worlds, the answer is often literal. Beneath the surface, there may be a sea. If oceans can exist beneath ice in our solar system, then the idea naturally expands beyond it. Around other stars, there are planets, and likely moons too, though exomoons are still extremely difficult to detect confidently. We have found thousands of exoplanets, many in systems very different from ours. Some giant planets may have large moons. If large icy moons are common, and if tidal heating and internal heat can maintain subsurface oceans, then hidden oceans may be common in the galaxy. This remains a possibility, not a confirmed fact. But it is a scientifically meaningful possibility. The galaxy may contain many worlds whose most interesting environments are invisible and far away. A telescope might see only a point of light, or perhaps infer a planet from a dip in the starlight. It may not see the moon, it may not see the ice, it certainly may not see the ocean beneath. The most important environment in a distant system could be completely hidden from our current view. That thought is humbling. It means the universe may be richer than appearance suggests. The places most worth wondering about may not shine brightly. They may be small, cold, covered, distant and quiet. A search for habitable environments may not be only a search for Earth twins under warm sunlight. It may also be a search for hidden water, for moons warmed by gravity, for chemistry beneath ice, for worlds where oceans are protected from space by frozen shells. Not every hidden ocean will be habitable. Not every ocean world will be friendly to biology. Some may be too isolated, some may be too chemically limited, some may freeze, separate, or remain sterile. We do not know. But the category itself is profound. It tells us that the universe has more than one way to make a water-rich environment. It tells us that Earth is special, but the idea of water in the cosmos is not confined to Earth alone. It tells us that habitability is not a single place on a diagram, but a set of conditions that can appear in different forms. As the journey continues, return for a moment to Earth's deep ocean. Far below the surface, where sunlight has vanished, pressure rises, and the water becomes dark, Strange animals move slowly. Microbes live in sediments. Hydrothermal vents release mineral-rich fluids from the seafloor. The ocean is not uniform. It is layered by temperature, chemistry, pressure, currents, and life. Even Earth's ocean has hidden worlds within it. The abyssal plains, the trenches, the vent fields, the ice-covered polar seas, the dark water under Antarctic ice shelves. Earth itself teaches us that an ocean can contain many environments, not just one. So when we imagine Europa's ocean or Enceladus's ocean, we should avoid imagining a simple empty layer of water. A hidden ocean may have currents. It may have chemistry gradients. It may interact with ice above and rock below. It may contain salts, minerals, dissolved gases, or organic compounds. Its pressure may be immense. Its temperature may vary. Its history may be long. We do not yet know the details, but the possibility of complexity is what makes these oceans scientifically rich. An ocean is not just a substance. It is a setting, a place where matter can move, mix, react, and change. Water is a remarkable solvent. It can carry ions and molecules. It can participate in chemical reactions. It can transport heat. It can dissolve minerals. It can freeze, melt, circulate, and store energy. It is familiar, but it is not ordinary. The more we study water, the more central it becomes to our understanding of planets. On Earth, water shapes climate and life. On Mars, evidence of ancient water helps us read the planet's past. On icy moons, hidden water may reveal interior environments. On comets and asteroids, water-bearing minerals and ice connect to the early solar system. Water is one of the threads running through planetary history. It does not always appear as an ocean. Sometimes it is vapor, sometimes ice, sometimes hydrated minerals, sometimes a plume, sometimes a buried sea. The solar system is full of water's transformations. Earth's ocean shines, Europa's ocean hides, Enceladus's ocean escapes in plumes. Titan's water may lie beneath methane weather. Mars remembers water in its stone. Comets carry frozen water through long orbits. Water is not just a feature, it is a traveller, a shapeshifter, a chemical companion to worlds. Let your mind drift again to Europa. The surface is quiet. Jupiter's light and shadow move across the ice. Deep below, if the models are right, an ocean rests beneath the crust. Perhaps the ice shell shifts slowly over time. Perhaps chemicals from the surface are carried downward. Perhaps minerals from a rocky seafloor interact with water. Perhaps not in the exact ways we imagine. The point is not to know tonight. The point is to feel the depth of the question. Europa does not give itself away easily. It asks for patience. It asks for instruments. It asks for future missions. It asks for humility. Now drift to Enceladus. The plumes rise softly from the South Pole, a pale spray of ice and vapor against black space. Saturn glows nearby, rings stretching across the sky. The plume particles are tiny, but they carry a story from below. An ocean is not only hidden there, it touches space through fractures. It is as if the moon has found a way to whisper. Not loudly, not completely, but enough to tell us there is something beneath the ice worth listening to. Now Titan, orange haze, cold air, methane lakes, dunes of organic-rich particles. A landscape shaped by weather, but not Earth's weather. Under the crust, a possible ocean of water separated from the surface by layers of ice. Titan is a reminder that worlds can be familiar in form and alien in substance. A river valley may look like a river valley, but the liquid may not be water. A lake may look like a lake, but it may be methane. The surface may seem strange, while below it, water may wait in darkness. Every world asks to be understood on its own terms. This is one of the gentlest rules of science. Do not force a world to be Earth, let it be itself. Europa is Europa, Enceladus is Enceladus, Titan is Titan, Earth is Earth. Comparison helps us learn, but it should not erase difference. Ocean worlds are not second Earths. They are their own kinds of places. They may hold water, but not our sunlight. They may have oceans, but not our waves. They may have chemistry, but not our biosphere. They may be habitable in some limited sense, or not at all. The beauty is in learning which is true. As we move deeper into this thought, the hidden oceans become part of a larger pattern in astronomy. The universe often hides its most important structures from the simplest view. Dark matter does not shine, yet it shapes galaxies. Exoplanets are often found not by direct images, but by tiny changes in starlight. Black holes are known through their effects on nearby matter and light. The interiors of planets are inferred through gravity, magnetism, seismic waves, or surface clues. Hidden oceans fit this pattern. They are not obvious. They reveal themselves indirectly, through induced magnetic fields, through plumes, through surface cracks, through gravity, through chemistry, through models tested against data. This kind of knowledge is quiet. It does not arrive all at once. It accumulates. A spacecraft visits. A measurement surprises scientists. A hypothesis forms. Another mission refines it. A theory improves. A world becomes richer. In this way, hidden oceans are not only physical places. They are examples of how science discovers the unseen. And perhaps that is why they are so restful to imagine. They remind us that understanding can be slow. It can be careful, it can be gentle. We do not need to know everything immediately. We can let mystery remain while still learning from it. Future missions to ocean worlds will continue this slow conversation. Europa Clipper is designed to study Europa through repeated flybys, investigating its ice shell, surface composition, geology, and ocean-related properties. Missions like Juice are studying Jupiter's icy moons, especially Ganymede, and will help refine our understanding of their interiors. Future concepts for Enceladus may one day sample plumes in more detail. Titan will be explored further by Dragonfly, a rotorcraft mission designed to study its surface chemistry and environment. These missions are not fantasy. They are part of the careful path of planetary science. They will not answer everything at once, but they will add detail. They will sharpen questions. They will replace vague wonder with specific wonder, which is even more powerful. Specific wonder says, how thick is the ice? What salts are present? What organic molecules exist? How much heat flows from the interior? How old is the surface? Where do plume particles come from? What chemistry is possible? This is how the unknown becomes a landscape. One measurement at a time. Now imagine, far in the future, a spacecraft flying above Europa's icy surface. It passes over long cracks, chaos terrain, and smooth plains. It measures the thickness of ice. It maps surface composition. It senses the moon's response to Jupiter's magnetic field. It sends data home. The signal crosses space to Earth, where scientists receive it, process it, and slowly build a clearer picture of the ocean below. Imagine another spacecraft crossing Enceladus's plume, collecting tiny ice grains and analyzing their chemistry with instruments more advanced than before. Each particle is small, but each may carry information from a hidden sea. Imagine Dragonfly lifting through Titan's thick atmosphere, moving from one landing site to another, studying organic chemistry on a moon where the surface looks like a dream of Earth, but belongs to a different chemical world. These images are not meant to make the video exciting in a loud way. They are exciting in a quiet way. They show exploration as patience with wings, as curiosity moving slowly across distance, as humanity learning to read worlds without disturbing their calm. There is also a deeper philosophical softness here. Earth's ocean is visible and alive. The hidden oceans are invisible and unknown. We live on the one ocean world we know is inhabited, looking outward at other ocean worlds, where we do not yet know what water has done. That is a humble position. We are not masters of the answer. We are beginners with instruments. We are a species from a blue planet learning that water may have many homes. This humility is healthy. It keeps the story safe. It keeps it scientific. It keeps it beautiful. We do not need to say aliens are there. We only need to say the ingredients are interesting, the environments are worth studying, and the questions are among the most meaningful in modern planetary science. Could life exist in a hidden ocean? It is possible in some environments, but unknown. What kind of life would it be if it existed? We do not know. Would it resemble Earth microbes, or be something chemistry allows in a different way? We do not know. Could some oceans be sterile? Absolutely. Could some be too isolated, too energy poor, or too chemically limited? Yes. The honest answer is not a disappointment. It is the edge of knowledge. It is where science is alive. The unknown is not empty. It is where careful discovery begins. And tonight, in a sleep documentary, the unknown can remain soft. We do not have to solve it. We can rest beside it. Let the journey widen again, beyond Saturn, beyond Titan, beyond the known ocean worlds, toward the idea of hidden seas in other systems. Around distant stars, planets form in disks of gas and dust. Giant planets may gather moons. Icy bodies may be captured or formed in place. Tidal interactions may warm interiors. Thick ice may insulate oceans. Some systems may have many moons. Some moons may be dry. Some may be frozen solid. Some may hold water inside. We cannot yet map them the way we map Europa, but the possibility changes the emotional shape of the galaxy. It suggests that some of the galaxy's most interesting places may be hidden, quiet, and small. Not bright stars, not giant planets, not spectacular nebulae, but moons, cold moons, icy moons, moons with surfaces that reflect pale light and interiors that carry darkness and water. It is a gentle idea that the galaxy may contain countless secret oceans, most of them unseen, most of them unnamed, each orbiting in silence around a planet under a distant star. Again, this is speculation, and it should be labelled as such. We do not yet know how common such moons are. We do not know how common long-lived subsurface oceans are beyond our solar system, but because our own solar system contains several strong candidates, the possibility is scientifically reasonable enough to inspire careful thought, and careful thought is enough for a peaceful night. Imagine a distant giant planet orbiting a red dwarf star. Around it, an icy moon turns slowly, its surface frozen under dim red light. Beneath the ice, perhaps water remains liquid because of tidal heating. Another system, around a sun-like star, may have a giant planet with several moons, some rocky, some ivy, some barren, some complex. In another place, a moon may have a thick ice shell and a dark ocean that has lasted for billions of years without ever touching the surface. These are not claims, they are possibilities, painted gently from what planetary science has already taught us. The more we learn, the more we realize that worlds are not simple. A planet can hide an interior ocean. A moon can shape a ring. A haze-covered surface can host lakes of methane. A frozen crust can cover liquid water. A small plume can carry the chemistry of a sea. A distant measurement can reveal a hidden layer. The universe is not only large, it is layered. The visible is only the beginning. As the script moves toward rest, let the facts become softer, but not disappear. Europa likely has a subsurface ocean beneath its ice. Enceladus has plumes connected to an ocean below. Titan has methane and ethane lakes on its surface, and may have a water ocean beneath. Ganymede likely has a deep internal ocean, possibly layered. Callisto may have a subsurface ocean under an ancient crust. These are not identical worlds. Each one is a different answer to the question, where can water be? And each one teaches that water in the solar system is more varied than a blue surface under clouds. The hidden oceans do not replace Earth's ocean. They make Earth's ocean feel even more precious. Earth is the only world we know with life. The only world we know with an open, living ocean under an atmosphere we can breathe. Its ocean is connected to rain, rivers, continents, weather, and biology. It is not hidden. It is part of the planet's face. When we return from thinking about Europa and Enceladus, Earth's ocean feels brighter. Not ordinary, but extraordinary. A visible ocean on a living planet beneath a sky that changes with clouds and seasons. The hidden oceans make Earth feel both less alone and more unique. Less alone because water appears in many places. More unique because life, so far, is known only here. This balance is important. It keeps wonder from becoming exaggeration. It allows us to admire Earth while still exploring beyond it. It lets us ask whether habitable environments exist elsewhere without pretending we already know the answer. It lets the universe remain open. Now, imagine one final slow pass through the solar system's ocean worlds. Earth first, blue and bright, its ocean open to sunlight. The moon nearby, dry and grey, a reminder that not every world holds water at the surface. Mars, red and cold, carrying evidence of ancient water in stone. Jupiter, immense and striped, with Europa glowing like cracked ice, Ganymede turning with hidden layers, and Callisto holding its ancient face. Saturn, golden and ringed, with Enceladus sending pale plumes upward, and Titan wrapped in haze, lakes, dunes, and possible deep water. The sun shines across all of them, weaker with distance, but still present. Gravity shapes their interiors. Ice protects their secrets. Water changes form. And the question remains, quiet and wide. How many oceans are hidden where we cannot see? How many worlds hold water under ice? How many moons carry seas that never touch the sky? We do not know. But the not knowing is not empty. It is a place for science to move gently. The answers will come slowly. A mission will launch. Years will pass. A spacecraft will arrive. Instruments will listen. Data will return. Scientists will compare, question, revise, and understand a little more. The hidden oceans have waited for billions of years. We can let discovery take its time. And now, as the voice grows softer, let the image of the ocean worlds become calm and almost dreamlike. Europa's ice under Jupiter's glow. Enceladus's plume rising like a pale breath into Saturn's night. Titan's amber sky above dark lakes. Ganymede's layered depths. Callisto's quiet ancient crust. Earth's blue ocean below clouds. Water seen and unseen. Water as ice, vapor, liquid, mineral memory. Water traveling through comets, resting in moons, shaping planets, reflecting sunlight, hiding in darkness. The solar system is not silent emptiness between worlds. It is a place of interiors and orbits, surfaces and secrets, light and shadow, ice and ocean. It is a place where the familiar becomes strange again, where water, something you may have touched today, also exists in forms no human hand has ever reached. The glass of water beside a bed and the hidden sea beneath Europa are not the same environment, but they are connected by chemistry, by atoms, by the deep story of planetary materials. Something ordinary on Earth becomes cosmic when seen in the wider frame. That is the gift of this journey. It returns us to the simple world with deeper attention. A drop of water becomes more mysterious. Ice becomes more meaningful. The ocean becomes not just a feature of Earth, but part of a larger question written across the solar system. Let that question remain gentle now. There is no need to answer it tonight. No need to imagine too much. No need to force certainty where science is still unfolding. Just picture a moon under distant sunlight, a frozen surface, a crack crossing the ice, a dark ocean below, held in place by gravity and time. Picture a small spacecraft drifting past, listening with instruments. Picture data traveling home across the quiet. Picture scientists learning, slowly, carefully, without fear. And picture Earth turning beneath you, its own ocean moving under clouds, its waves crossing moonlit water, its deep currents flowing through darkness. You are on the one ocean world we know best, the one that gave you breath, weather, rain, and life. And from here, humans look outward, wondering whether the water story continues elsewhere. The hidden oceans remain hidden for now. They do not need to be solved to be beautiful. They do not need to be inhabited to be meaningful. They are part of the solar system's depth, part of the way worlds can surprise us, part of the quiet truth that surfaces are not always the whole story. So let the day loosen, let the mind drift outward past familiar coastlines, past Earth's blue atmosphere, past the Moon, past Mars, toward Jupiter's icy moons, toward Saturn's small white Enceladus, toward Titan's amber haze. Let each world pass slowly, peacefully, like a thought floating across a dark sky. Europa beneath ice, Enceladus beneath plumes, Ganymede beneath layers, Callisto beneath craters, Titan beneath haze, Earth beneath clouds. Water everywhere in different forms, asking different questions. The solar system continues its quiet motion. The moons continue their orbits. The oceans, seen and unseen, remain where they are, dark, cold, hidden, patient. And here, on Earth, under the soft turning of night, you can rest beside the mystery, not needing proof beyond what science can give, not needing answers before their time, only resting in the calm possibility that the universe is deeper than it looks, and that somewhere beneath the ice of distant moons' oceans may be moving slowly in the dark,